Okay, so for our candy grab activity data, looking at how we're going to present the information for our scatter plots and correlation notes, right? The data present the number of candies grabbed by each of 11 students and their hand measurement, right? So we have the candies grabbed, we have the hand spent. We're asked to sketch a scatter plot of the data by hand and comment on any collection information that could have improved your scatter plot, right? And really, when we're drawing a scatter plot, we should also talk with the relationship that we see, right? So I've drawn the scatter plot here, and one of the things that I did to help me draw the scatter plot was first identify on the candies grabbed my minimum and my maximum value, so I could set up my scale to make sure I saw the minimum and included the maximum. Right? On these scatter plots, it is okay to break the axes. Right? It is important that we label the axes. And of course, the comment on collection information that could have been improved. Well, what type of candies did we grab? Different size candies, right, may affect the type of correlation that we have, or maybe not. But knowing the type of candy would help. What about the hand span? What's the measure of hand span? These are just some numbers, right? But are these inches? Are they centimeters? Are they quarter inches? Are they half? Like, what is this? My guess is they're probably centimeters, right? But if we're not sure, right, that can cause a problem for us later on, that measure, right? But we should have these labeled nicely. Now, how did I get this information on the horizontal axis? I came over here and I noticed, right, my minimum and my maximum value for this was 16.3 to 23, so there's my hand span. Now, why did I choose hand span on the x-axis? Right, because I might say that, hey, if I have a bigger hand, then that's going to lead to more candies being grabbed. Right? But very easily, I might have considered the explanatory variable candies grabbed to put it on the x-axis and say, hey, if I know how many candies you grabbed, then I can probably talk about how big your hand is. Okay, so this relationship, how would we state the relationship in this situation? Right? Well, for this situation, we could say that we have either a strong or moderate positive linear relationship, right? That if we come over here and we look to kind of draw a line, see what it might look like, right? Think about, hey, where might a line go? What might I have? Right? These two values seem to kind of drift off a little bit. I got, a few values close together there, right? That, this may be a strong or a moderate correlation. We're not quite sure, but definitely it seems to be positive, and it does seem to be linear for these hand span measures. Right? And this is the relationship between the hand span and the number of candies grabbed. Always make sure that you talk about the strength, the direction, and the linearity. Okay? Then, our next step involves the use of a calculator. So I've taken the time to put my information in the calculator, and here I have my candies, and here I have my hand span. Right? And I want to calculate the correlation coefficient, the coefficient of determination, and the equation of the least square regression line using my calculator. So I'm going to come in here, right, put the information in my table, but I have to remember that when I'm going to come and do my linear regression, right, my x list is not L1, right? My explanatory variable I had in L2, right? That this hand span I called my explanatory, so I've got to make sure that I adjust that. And then my y list, L1, right? My y list is L1, and I'm going to go ahead and store the equation in alpha trace. I'm going to store that equation in y1. Right, so I'll come over here and I'll calculate my linear regression. And I look at this linear regression and I see that I have the following. Right? I have y hat, that's going to be my linear regression, y hat equals negative 8.19 plus 1.645 it looks like, so 1.65x. But what about the coefficient of determination and the equation of the least squares regression and the coefficient of determination and the correlation coefficient? Well, to get that, I need to be able to set up my calculator to turn on the diagnostics. So if I come over here and I go to my mode, right, then I need to make sure that I come down and I do turn on my diagnostics. It's always a good thing to check at the very beginning when you're using your technology that you have everything set up how you want it set up. Right, so now if I do my stat, calculate linear regression, once again, make sure your X list is right, make sure your Y list is right, come over, right, I'm going to store that regression equation into alpha trace Y1, calculate, and now I see my R and my R squared values. So I'm going to go ahead and write those values down. So I have that R is 0.75 approximately, and R squared is 0.57 approximately. Okay. Now it's not going to be the case that these are always flipped. That just happens to be the situation in this particular case. Okay. So what does this mean, and what else do we need to do here? Well, this y hat, this is my least squares regression line, but it's always good to define my variables, right? Y hat is the predicted number of candies grabbed, right? And X is the handspan in, we're going to say, centimeters, right? R is that correlation coefficient. R squared is that coefficient of determination, okay? What does R squared represent? R squared represents the percent of the relationship of the predicted value that can be explained by the linear model. Okay, and my R, we can talk about what that represents, but really want to say, hey, right, is this R what we stated in terms of being strong or martyr? Remember that we talked about that for our purposes, we're going to say a correlation of 0.8 is strong, and that a correlation of 0.5 can be considered as weak. Okay. Well, 0.75 is really close to 0.8, but it's less, so it's kind of fallen that. All right. Now, know that some will say that a 0.7 R is considered strong. And some will say that a 0.3 R is considered weak. So you got to be careful, right? Our general will be this, but be aware that these are common standards as well. Okay. Now, interpretation of the slope and the y-intercept in context. Well, in context, the slope would mean that for each unit change, and specifically increase, for each unit increase in the handspan, the number of candies grabbed increases by 1.65 on average, right? That for each increase in this explanatory variable, y hat, the predicted, right, will increase by 1.65 on average. Now, for this one, this is a situation that the y-intercept has no meaning, right? It's not part of the explanatory data range, right? The y-intercept is, hey, the handspan is 0, right? We don't have anything about the handspan being 0. We might look at the handspan maybe down to 10 centimeters. Maybe not, right? We're not quite sure. Maybe up to 25 or 30 centimeters. Maybe not, right? But between 16 and 23, we're going to feel pretty good about our decision making, right? But at 0, that's too much extrapolation. And if we actually think about how to say it, if the handspan was 0, negative 8.19 candies grabbed, yeah, that makes no sense. So in this situation, the y-intercept has no meaning. Okay. What about the calculation and the interpretation of the residual for the first student in the list? Okay, so if we want to calculate and interpret the residual for the first student in the list, y minus y hat is our residual, right? First student in the list was grabbed 22, handspan 19.1. So we can come over here and we can say, hey, 22 minus, right, the formula that we had, negative 8.19 plus 1.65 times 19.1. I had an x in there and I had to adjust it, right? So those of you that can't see that, that's 19.1 that we were multiplying by in there. Okay, we do that math, that's 22 minus 23.325, which is negative 1.325. And what's the interpretation, right? That the student actually grabbed 1.325 fewer candies than predicted by our linear model, right? That our linear model predicted they would grab 23, right? They only grabbed 22, okay? Now, let's construct and interpret a residual plot for the candy grab data. All right, there's going to be two ways we can do this on our calculator. All right, one way that we're going to be able to do this on our calculator is to go stat edit and put our residuals in here. All right, well, how can I get our residuals? It's going to look very much like what we did here. All right, that we're going to say our residuals are going to be list 1, that's the y, minus, right, then parentheses, because it's going to be minus y hat, and that's negative 8.19 plus 1.65 times the numbers that are in list 2, right? That it's going to be at each of these x values, what's going to be predicted? Well, that's the y hat. I set that up, press enter, and boom, it spits out my particular values. I could also come in here and calculate my residuals in a different way. Let me come to L4, go up to the top, and I'm going to hit second stat to get to the list, and look down here, we see the residuals, right? And I'm going to say, let me put all my residuals into list 4, and notice that these match closely, but there is a little bit of differences, and those little differences are primarily due to the rounding that we had here, okay? So really the list 4 is going to be the better one to use, okay? But now what we need to do, second stat plot, we want to make a scatter plot, turn it on, right? And our scatter plot is going to be the x list of our x values, that was L2, and the y list being those residuals. Well, those residuals we had in L4. If I hit zoom 9, there are my residuals, and I look at this, and there doesn't seem to be really too much of a pattern here, right? Fairly nicely distributed here and here, right? Here's those two values where the hand span was a little bit larger. And if we go second stat plot and we say, well, what if we did the residuals from those rounded values and we graphed? Notice that there really isn't much difference there, right? Those little decimal places aren't going to do much, right? But there's no real clear pattern to what we have here. So that would be our construction of the residual plot, and our interpretation of the residual plot would be that we have, right, randomness to our residual plot, and therefore a linear regression is appropriate for this data. Okay, the linear regression is appropriate for this data based on our residual plot. All right. So as you have questions, please make sure that you ask them for clarification. There's a lot of information in this unit, but the practice will help you improve.